Okay, so very good afternoon to all of you. So this is our lecture 9 on this topic of energy management in grid integrated solar PV based smart charging station in presence of optimized battery energy storage system. Now I will mainly concentrate on the microgrid. The charging station essentially is because that microgrid is also considered as a point of charging of that e-vehicle. But not only the e-vehicles, there are other loads also, right? So I divide this total part in two categories. One is this energy management, and other one is this optimized BSS, right? Energy management and optimized BSS. So this particular topic is related to one of the project funded by the DST and European Union. It's a collaborative project where several institutes and industries from either side of the country they are actually involved, and it's kind of a deployment project. So what was the aim of that project is to deploy the actual microgrids in two sites in India. One site is in Ghoramara Island, which is in West Bengal, and other one is in Keonjhar, which is in Odisha. So those are the two states have been chosen where the utility grid has not reached. Means the inhabitants or the villagers, there are actually few villages in those two areas. So the villagers has till date doesn't have that essence of that electricity. So we are providing them the electricity through these deployment of microgrid. So it's a very technically satisfaction as well as humanitarian ground from that also is there. Okay, so it's a very satisfying project. It is going to be end this year June. So these are the Indian parts. Nothing was there, and we are going to deploy microgrids. And from the European perspective, there are two locations. One is in Greece, another one is in Denmark. So there are islands, and those islands are already having microgrids. But those microgrids need to be made smart. Okay, smart means there must be some kind of an communication for the purpose of benefiting and operation of this particular microgrid in some better manner. So my part was to looking after this energy management tool, which involves from the very beginning. I yesterday talked about that forecasting of the energy vectors. So that forecasting is a major issue because all these microgrids are having energy sources, and majorly the distributed energy sources. There are solar, there are wind, there are energy storage units, there are biomass, biogas, gas turbines, and so on and so forth. So each of these microgrids are having a cluster of different energy vectors along with load. So the loads again can be categorized as that household, maybe for a small market, maybe there is some schools and hospitals and electric vehicles, of course, right? So there are different kinds of loads. So we are categorized those loads and the time frame, the load profile can be achieved. But as because from the Indian perspective, there was no electricity, so there was no load. So there is no historical data for the load. So we are providing the loads and how much the way that loads are being utilized. So we are creating the profile from our own. Right, so the variation of the load is basically can be considered as the actual load profile. There is no option of prediction as far as that Indian islands are considered. But for the European side, there were loads, but again those loads are the data were not recorded anywhere because those microgrids are not smart microgrids. So the data were unavailable. So only the energy vectors which has that option of the predictions are basically these energy sources. Right. So going forward, this is the workflow of the problem that I was supposed to look after. It's basically first the system design, and then there are two parts. The system design having these two aspects. One is this forecasting, which includes load, solar PV, wind power generation as far as the Indian sites are considered. And system stability. I'm not concentrating on this particular block today. And then this forecasting, after forecasting has been done, there are options of demand response and then demand side management. And then this system stability has two parts. One is this microgrid stability. Microgrid, if it is a DC microgrid, so there are basically DC and AC, both microgrids are there. So if it is a DC microgrid, what do you mean by that stability of the DC microgrid? What is that stability? Stability of what? If it is DC microgrid. Normally, if it is an AC system, the stability refers to that angle of the generation, conventional synchronous generation, right? But it's a microgrid where the generating sources are solar and wind, right? And they are also converted to a DC quantity. Solar is directly connected to the DC grid through some chopper, of course, and wind is converted, that AC is converted to DC and then connected to the node point. So where is the point of that stability? It's basically the voltage stability, the magnitude, and that even is not stability. To be very specific, it's the voltage regulation that we are talking about. So we are concentrating the magnitude of the voltage to be within some acceptable range, right? So we are regulating the voltage. So, and this black start, the background of this block is also black. So what is a black start? Black start is something that we are starting from zero. So it can happen that when we are first switching on that system, or maybe it is operating for a period of time and then something has happened, maybe some natural calamity or so on and so forth. So what will happen that we need to shut it down, and then again from zero I need to start. So what are the actions need to be taken, how the converters and the inverters will work, because each of these generating units are connected through some power electronic interfacing. So whether there will be a grid follower or the grid forming converters, right? So if it is a black start, it cannot be a grid following because there was no grid at all. So the converters need to operate or the control in such a fashion that it can form a grid. So it is a grid forming converters, right? Instead of a grid following. So the converters are basically of these two types, in the sense that whether it is connected to a grid which is existing, so it's a following that grid parameters and the variables. So it's a grid following converters, or it is forming the grid, right? So it's a grid forming converter. So for black start, the strategy is that it should work in a grid forming fashion. So these two are not the topic of our concern today. So we'll concentrate on these upper portions. Okay, these are not visible properly, but it's a development of overall control algorithm, because whenever this box is done, then this data will be transferred for the development of the overall control algorithm and then implementing and testing and deployed at that Indian demo sites. So this is for the Indian demo sites. That's why we are seeing that there are solar PV and wind power, but of course there are biomass and biogas. So this is the background that we have created, and then coming to the overview of today's presentation, which is having this energy management and demand side integration. But in between, I will also talk about that battery energy optimization. So energy management, it involves that efficient utilization, monitoring and control of energy resources. Battery and other storage devices are also need to be there as a backup. And then demand side integration, I already talked about yesterday, that we are basically including the load for the purpose of that management of the energy, right? So load, the customers can also take part while we are managing the energy, okay? So we are giving you that customers, the operators are giving some particular time frame, asking that this is a very critical time frame, because the energy sources are having a lower energy side and the loads are pretty high. So either you curtail the load or you shift the load, so that I can make that balance of energy, right? So that's a demand side integration. So I need to know that what is the grid condition, the pricing signals, availability of the renewable energy. So all these will ultimately determine that what should be the way that this exchange of power and the exchange of money will take place. So what are the challenges that we are facing is that renewable energy integration, the first and foremost challenges, whenever we are integrating some renewable sources, that itself is a challenge. After integration, the challenges are there, but connecting and renewable source itself is a challenge. Then energy storage and grid stability. So for the purpose of that stability, we are using that energy storage, because whenever we are seeing that this may be the variation in the sources, this may be the variation in the load, then you are just find out the deficit between these, the difference between these two two lines, two variable lines, that should be the way that the energy storage will have its own way of power line. So economic factors, then these technological and operational complexity, regulatory issues. Of course, you cannot avoid that regulatory issues and that feasibility and the social aspects. The problem with these kinds of projects is that it's a deployment kind of a project. It's not only making a prototype, right? It is not in the laboratory. It is already deployed, and which can have a support for a certain period of time. The technical support can be given for a certain period of time, because the funding agency have a limited fund with us. Okay, so after that, if that should be sustained, then the local people need to be trained. Otherwise, that sustainability will vanish. Okay, so that's another challenge. That's a social aspect. So how much feasibility? So it should not be very complicated. Only 2-3 points of operation will ultimately make the feasibility of the operation of the whole system. That's again another challenge. So how to make it simple but doing some complex work. Fine. So problem statement is that energy management tool for energy vectors like wind and PV, and performing forecasting and demand response using a machine learning algorithm, and then aim to develop an energy management tool for isolated microgrids. So that's the important part. Isolated microgrids, they're not connected with the grid. If it is connected with the grid, then anywhere there is a problem, then there is a grid assistance which is available. But there is no such grid is available. Energy vectors, forecasting and demand response, these are the three aspects that we are looking for. So objectives are that should be capable of serving any microgrid, should allow, so any microgrid means there are 4 sites as I was talking about, 2 are in Indian side, 2 are in the European side. So the strategy should not be different for different sites, because it's a single project. So your strategy should be of a single kind of an, I should say that the code can be different, but whenever the operator will think that I am sitting at this site, I want to manage this particular site, so I should be ready to deal with the site situation. So it should be generalized in that fashion. Should allow integration, and should be adaptable to various load and energy vectors. So end-to-end product to cater all the needs of an isolated microgrid. So the coding and all, it's a back-end kind of a thing. So we are writing some code and it will work, taking some input, giving you some output. But if that requires some technical knowledge, so to deal with that codes. But the people who are using it, or the end user, they don't have that technical knowledge. But they must know that how it can be run. So suppose we are using some mobile app. So you don't know that what is there inside that app, what is the programming inside that app. But I know that the interface is so easy to understand that you do this and do that and do this. So the steps can be easily understandable. So that's a front end. So that is also our task to make that front end. Okay. So it should be user friendly at the same time. So end-to-end product to cater all the needs of that isolated microgrids. And that front end should have 2 purposes. So it should allow that whether, it will ask first that whether you are an operator or you are a customer. So operator can have that ability to create that demand response critical window, right? And then he will decide that what should be the incentive corresponding to that critical window. If the fellow is taking part in the demand response, then what should be the incentives? If it is not, maybe again, taking part means there are options that whether you are load shifting or whether you are load curtailing. Okay, so depending on that, the incentives are decided. So that's the part of that operator. Now the customer, he will see that, okay, this time I can take part, I will get this kind of an incentive if I am taking part in this with curtailing or shifting, right? So that kind of options are there. So there are 2 different aspects of these front end part. So as I told, it's at U India Reimport project, which is funded by, from the Indian side it's the DST, and from the European side is the European Union. Giving a brief overview about the islands. The first island is this Ghoramara Island. It is in West Bengal. I don't know, this is legitimate. Is Is it clear to all of you? Can you able to see this? Okay. So it's in West Bengal, India, located 92 kilometers south of Kolkata, India, in the Sundarban Delta area. Okay, you know that Sagar Island. Have you heard that Sagar Island? Okay, so just like Kumbh Mela, there is one Sagar Island in Makar Sankranti, that Mela was being there. It's not so popular, but having the same that rituals and the religious aspects is there. So Sagar Island is quite famous. For long period of time, even if there are people are coming in each and every year for that in the Sagar Island, but it was not electrified. Okay, now few years back, that electric poles are been created from the Kagdip area, which is connected with the land, and then through the water, that electrified poles have been gone up to that Sagar Island. So now electricity is there in Sagar Island, but this Ghoramara Island, it's not that much of importance is there, so nobody cares about it. Okay, so this is the Ghoramara Island, which is our target area. Now, where there are solar PV, so it is decided that depending on, again, that engineers or the technicians, they are governed by the money, whatever you are getting. Okay, so I need to decide that how much solar power, how much wind power, what are the loads and all that I will provide to that customer. Okay, so on that basis, the area which is available. So we had a talk with the panchayat of that particular village. There are basically 4 villages, 1100 houses. So we had a talk with them, and then I understand, okay, there is a school which is a primary section and the secondary section, that the school area is available, which is near to the that river. So we can install the rooftop solar as well as the land can be occupied for the solar plants and all, and the wind turbines installation. Along with, there is a room for the battery energy storage system. So all these need to be take care. So depending on that, the availability of the area of the land, we are having that solar module power, which is 540 watt peak, and then wind turbine, which is 5 kilowatt. Battery is 240 numbers with 2 charge single in parallel, so 2 volt 750 ampere hour. Consumptions, so as I told, that categorized of the loads are these non-critical loads, which are the residential households, and then there are market, school, which is commercial load, and hospital and poultry farm can be considered as a critical loads. Poultry farm, why this is a critical load? Because 24/7 that bulb need to be glowed, right? So that's why it's a critical load. Okay, and hospital, I should not say it's an hospital, it's kind of an health center like our in campus. Okay, but whenever there is a need, the electricity must be there. So consider that load to be as a critical load. Historical price data, it's not applicable, it's not available. Okay, N stands for not available. Okay, okay, the tariff that we are deciding to make this is sustainable, I need to ask some money from the customers, of course. So for the beginning, it is not decided. Dynamic pricing was not there. Okay, dynamic pricing was not there. It's 50 rupees per month per house. Assume that 1000 houses for calculation purposes. So as I told, there are 1100 such families are there. And then the commercial is rupees 100 per month per load. Assume 6 commercial. Okay. And also there is another aspect of that connection of that electric vehicle. Those 3-wheeler electric vehicle that we are providing from that project fund only. We are providing, and along with that there was one electric boat. So that electric boat is a solar PV based electric boat that is also connected that Sagar Island, the Ghoramara Island and the Kagdip, which is part of that land. Okay, so that electric boat is also provided, and that is again solar powered battery assisted electric boat. So that will also charge from this grid only. Climatic condition, that is the major problem. So you go there and you will find out beautiful that scenery, right? But it's not for stay purposes. Okay, you cannot stay there for a long period of time. 1 day, 2 days, that's enough. Okay, it's over and then you come back to your home. Otherwise, you cannot survive. So you just imagine that the condition, that how these villagers are living for years after years. So this is cyclonic area, and it was written that extreme weather conditions every 2 to 3 years, but now the scenario has changed. You will see that this kind of cyclonic weathers are coming in 2 to 3 times in a year, right? So there are so many names have been given, Ayla, Laila, and there is a long list of these such kind of names, right? So this is coming in each and every year, maybe twice or thrice. So, and that is affected. This area was quite affected because of this portion. So that wind turbine, it's not an electrical part, but the wind turbine is installed with that resilience with respect to this extreme weather condition. So even if there is very high wind, the structure is still rugged there, and it will not disturb, right? Even if we are not producing power from it, but the structure is still should be there. So it is weather resilient from that critical condition. Keonjhar, again a beautiful scenery. So we have visited, and it's, you'll love it. It's on a hill and then inside a jungle. So it's a beautiful area to rove around, not to live. Okay, because there is again no electricity. But the people are so kind. So the area is 202 hectares, 75 houses with 300 population. So nobody cares, right? Nobody cares. Cares from that sense, it's not that it is inhuman, it is uneconomical. To install that or to cater that utility grid till that point, it's uneconomical, right? So the only option is that you create a microgrid there. So there are climatic condition, it's hot with humid, and total capacity 30 kilowatt peak. Biomass and biogas, as I told that there are biomass and biogas, there was no wind installed, and electricity tariff is something different because the number of customers are different. So it is different, and again the economic condition and the panchayat discussion with the panchayat, so it was decided on a mutual basis that what should be the tariff of that electricity. Bornholm is the another location which is in Denmark, Bornholm. So already there was some microgrid, and there are the local area was electrified through that microgrid, but the purpose of this particular project is to make that microgrid smarter. So there are approximately 1000 rooftop solar PV system contributes 8 megawatt, and to privately owned solar PV production facilities with 15 megawatt with an additional of 20 megawatt PV plant under development. There is a biogas plant, there is a wood chip powered boiler generators, and fossil fuel generation has a capacity of this. So number of energy factors. There are several number of different energy factors are associated with that microgrid. And Kythnos, it is in Greece. Basically the area is the Guidamara, and Kythnos is that Kythnos in Greece, close to the leading institute in the European side, which is the NTU, National Technical University of Athens. So Kythnos is close to that. So it is again an island. This is a view of that island. So number of inhabitants are 1608. So this is a pilot led by this, as I told you, that NTUA. So 238.25 kilowatt solar PV stations. Wind energy is also there. Each one is having 500 kilowatt, totaling 665 kilowatts. So that's some overview about of these 4 sites. Coming to that, what is my EMT? So it should monitor the system, means the solar irradiance, the temperature, and the wind speed, right? And then a certain ML algorithm will apply it, and we can able to understand that how much we can forecasting the loads. We are forecasting the sources, right? But the thing is that whether we'll go for a 24 hours, means a day ahead basis load forecasting, or the energy vectors forecasting, is it enough? If the microgrids are connected with the utility grid, then the forecasting in a day ahead basis is okay. But if these are isolated manner, then anything can happen within a short period of time. So the forecasting with a shorter time period will make the things much better for the management of that energy, right? So that's why not only 24 hours, we have forecasted energy factors for 6 hours ahead. So which is pretty close to each other. So you can take a decision knowing that what will be my node after 6 hours, right? So that 6 hours ahead forecasting is also one of the strategy that was developed through this project. Now this utility algorithm means the load, the time frame for participants, the demand response. So I should have that ability to understand that whether I am taking part in the demand response or not, what is the critical window for which I am taking part in the demand response. And that or utility, they will decide that, and consumer, they will participate it. And the pricing algorithm, whether I am getting some incentive out of it or not. What will be my bill after 1 month, electricity bill after 1 month. So this is related to that the data set. Okay, how much data set what we are having. So we are having data set for PV and wind, but we don't have any data set for the load as far as the Ghoramara side or the Keonjhar side is considered. For Bornholm also, as I said, that it is unavailable. Assumed a random load profile based on the daily energy generation. Knowing that these are the different loads, it is already there. So we have generated some data points. And for Kithnos also, it is unavailable. So those sites are still having that microgrid, but those not recording that load. So they are not smart enough. So we are making them smart now. So PV and wind everywhere it is available, but this site is not having that wind. So we are having that biomass and biogas. But again, we don't have that historical data set for this, because for the first time it is going to be installed. So I'm not going into the details of this. Only one thing just I want to tell about that that energy management tool, which includes that forecasting of the energy vectors, it always need to be modified after certain period of time. Why? Because we are understanding with some sensors, okay, this is the actual solar insolation, this is the actual wind speed. We are predicting it, and always there is a comparison. The accuracy is something that is acceptable in that range. After certain time, we are getting that data, right? The actual data are there. So I can feed it back to my data file. Okay. So those are the actual data, which is the recent data, which is having much more impact as far as that my recent forecastings are considered. So we are always having that recent data, which is modifying my data file. Right? So that is taken place at each and every 1 hour basis instance. So all these data files are modified at each and every instant. Okay, for each of these features. And then after certain period, I have a lump sum amount of data. So why not to train your ML algorithm again? So we trained our ML algorithm again for expecting that accuracy will be more. So that is the thing that we are adopting here, and we are doing it. And then you have a limited memory of your data file. So after certain period of time, what you can do that the oldest data can be curtailed from your data file. Okay. So you are taking care of that memory which is available with you. And the techniques could be anything which is giving you the best results. ML techniques, there are ample of ML techniques. I yesterday talked about certain techniques. So those techniques can be used. Here mainly we are focusing on either LSTM or in combination of LSTM with some others. I don't know whether it is again visible or not. It's about the Ghoramara Island PV generation and the wind generation. And this is the load profile. So it is not predicted, it's just created. The load profile has created. This is for Bornholm and Kithnos, a few of the data plots about that PV and wind. So see, this is my PV generation, this is my wind generation. Almost there is no wind for that particular day which is considered, then the total load is something like this. So this is that difference. This is the difference that will create the importance of the energy storage. Okay. So whenever I am talking about that energy storage is included, now that battery energy storage means we have considered for this particular, there may be several kinds of energy storage units. That's a different story. We can have battery, we may have a super capacitor, we can have a superconducting magnetic energy storage, we can have flywheels. Options are there, but for this particular project there is battery. So now battery is there means on several factors, because it really costs a lot, battery energy storage. So we need to take care while we are installing, while it is operating, we need to take care of the cost involvement in that project. Okay, so you cannot ignore that operating cost also. So on what factors, what do you think that on what factors the life of that battery is depending on majorly? Charging and discharging cycle, right? So as many number of charging and discharging cycle, maybe the frequency of that charging and discharging cycle. So if it is more, then of course the life will be short. Anything else? Environment means majorly the ambient temperature or maybe the operating temperature of the battery itself, right? So those are the two major factors which are affecting the life of that battery. So we have considered, again I am borrowing few slides for this optimized battery energy storage from my student Dipanshu, but I should not say now, he is not student now, my earlier student. So I am borrowing some slides from his work. So battery energy storage system, this is a very popular equation, mathematical modeling of the BESS, considering this is the equivalent circuit of BESS. So it can be used as a source, it can be used as an emergency backup, it can store energy, it can generate energy as and when needed. So the terminal voltage can be expressed with the help of this equation, right? Where normally I know that this ampere hour is the rating with which we are normally giving the rating of the specification of the battery with this ampere hour. Now model of battery energy storage, it's a pretty popular model, capacity fed. The very name suggests that capacity is fading. Whatever the capacity at the beginning of that battery is having, it is faded with years, with ages, right? So the model which includes that capacity fed is known as that capacity fed model of BESS, right? So that involves certain factors of this DOD and SOC. The full forms is depth of discharge and state of charge. Depth of discharge and state of charge, along with the temperature and the charge discharge rate as we are discussing, right? So just have a look that how this capacity fed versus time, the variation in charge discharge rate, right? So you see that it is C by 2, 2C, 6C and 10C. You know this? This 1C means what? If I say that the ampere hour is given, 10 ampere hour means what? 10 ampere in 1 hour, right? 10 ampere in 1 hour. So that is 1C. That is 1C. Okay. So if it is operated with C by 2, if it is operated with twice of C, if it is operated with 6C, 10C, then how the battery life is having that impact on that discharging rate, charging discharging rate. Okay. So this particular picture will show you that you go on increasing that charging discharging rate, the fade will be more. It is increasing with that fade, okay, which is expected. And the next one is that with respect to the temperature, right? If the temperature increases, then for a particular charge, so it is fixed at C. It is fixed at C, and for that particular charge, how it is having that impact on the life of the battery, so how the capacity is faded. So that is being shown. So go on increasing the temperature, we will see that it is going downwards, that the characteristics is going downwards, right? It is first it is fading. The model includes that the dependency of SOC is neglected, and so cycle life model to study the impact of the temperature and DOD. So this is something that we are looking for. And inclusion of SOC will somehow, so there are some alpha and beta, so fitting coefficients and then the compensation factor. So these things are already available in several literature. So I'm not going in the detail of that. Only information is that it is for a lithium-ion battery that was being considered for the study. Okay. So you can modify your Q loss by inclusion of this state of charge behavior. So lithium-ion battery is having this kind of that cycle life. Okay. The capacity fed model also includes the severity factor mapping. So the end life of BSS. What is the end life? Can you predict it? What is the end life of that battery? So for that to calculate, you have that H nominal, and we have that the indicates the ampere throughput when subjected to realistic condition, right? So this is H nominal, and you can consider that this is the actual condition ampere hour throughput for the actual condition. So when Q loss with that end of life is considered to be 20% and indicates that is the end of life of BSS. For this particular study, we have considered that is considered to be 20%. This particular figure I showed yesterday, that taking some inputs, I am passing it through some filter for that pre-processing of the data, and then some LSTM autoencoder is giving you that forecasted insolation. But it is not only the insolation; it could be any variable such as wind speed also. So that LSTM AD model for forecasting, and then this was also that yesterday's plot that we are having, that actual and the forecasted plot. If this is the load profile, then I am getting some kind of a deficit power. So that will determine that what should be the charging discharging cycle of the battery in a particular day. So how the sizing of the battery energy storage can be determined with this flow chart. So we are finding out that difference, and then we are seeing that whether this difference is greater than 1 or not, then that battery power is equal to the deficit power. If it is no, if it is yes, then we'll check for that it's whether it is greater than certain maximum value or not. So this P battery, and if it is yes, then this P battery is equal to the 0.25 of that deficit power, and P grid is equal to 1 minus the P battery, because it is grid connected. So it was this strategy was not for an isolated microgrid. This is for a grid connected scenario. And if it is no, of course, then your P grid is 0 and your P battery is equal to that P difference. So as incentive based that demand response program, is yesterday also I was talking about this. This talk is also involving that energy management with respect to that demand response. Now demand response actually reducing the loads, right? It will ultimately reducing the load. So if it reduces the load, then the battery discharging cycle or the discharging power will obviously be reduced, because the deficit will reduce, right? So if the customers are taking part in demand response, then basically in other way we are increasing the life of that battery, right? Are you getting this? When the customers are taking part in the demand response, so either they are curtailing the load, considering that they are curtailing the load, then the stress on the battery is obviously reduced. Okay, so stress of the battery reduced means the charging discharging cycle frequency, it is now decreased. Charging discharging cycle frequency is decreased, so the end of life will increase. Okay. So the incentive scenarios, there are 7 incentive scenarios as created, and this is the load demand profile. If you consider for that study, then it can be divided in this valley of peak and peak period. So there are certain incentive scenarios from the load profile attributes and the economic attributes. It can be seen that when my incentive is that 20 cents per kilowatt hour, then this is creating some optimum scenario. How it has been determined? It is determined from this plot. It could be easy to understand from this plot that you see that that service provider revenue and the prosumer benefit beyond this S3, which is 20 cents per kilowatt hour, the part of this prosumer benefits, it is more than the service provider revenue. So that is again not desirable. Okay, it is not desirable. So we are stick to this up to this incentive. So that is the critical incentive. So it is in a win-win situation. The customers will also be happy. The service provider is also happy that I am also making some profit and I am getting some incentive. The customers will think like that. So that's why this is the critical incentive scenario as far as that IVDA policy is considered. But at the same time, if the customers are reducing loads, then they are basically sacrificing the enjoyment of the electricity, at least for certain percentage, right? So there is one index which was also considered, which is known as that discomfort index. Okay, so if the discomfort increases, means the customers will be angry. So the discomfort, depending on that, you are actually compromising that. So the satisfaction or the discomfort, you are compromising on that. So you cannot take part where you consider, even if the household considers to be that non-critical load category, but of course to me my loads are critical. Okay, from the operating point of view my loads are non-critical, but at least to me my loads are critical. So I am enjoying some electricity, I have that connected load, so why not to use as per my wish. But again, if I am getting some kind of an incentive, I will take part, but not fully. So how much I am compromising, so that can be find out with the help of that discomfort cost. So the discomfort cost is pretty high because they are taking part more and more with that consideration that I will get more incentive. So when you will get more incentive, you are taking part, because if you are curtailing load more, then you will get more incentive. So on that respect, this again, that S3 is considered to be pretty realistic. So again, continuing with this capacity fed model, so we have found out from those equations that how many such lithium ion cell will be required, what would be its nominal that ampere hour throughput, and then what is the number of cycles for this, if I consider that my DOD is 0.75. So we have considered the range of the state of charge from 0.2 to 0.95, and the and C rate is C by 2 to C by 20. So it's not C, it's either C by 2 or less than that, taking care of that life of the battery. So these are the details of the fitting functions. If you can remember that earlier slides, it includes some alpha, beta and eta. So that fitting functions along with that E, A, R and Z. So those fitting functions are given here. Temperature variations are also considered, because ambient temperature plays some vital role deciding that that life of the battery. So that summer is having some minimum, maximum and average temperature, mild weather and the winter, and this is showing that severity factor with respect to that C rate and SOC, how it is varying. Okay, the severity factor at different temperature. So it is quite having some impactful scenario if the temperature is varying from -5 degree to 40 degree, right? So it has a major role to play to decide the life of battery. But if you consider that SOC, so 0.2, 0.35, 0.55, 0.95. So as I told, that SOC range is considered for 0.2 to 0.95. So see the layers, how it is differing, the severity factor, how it is differing if that SOC is different. So with respect to the temperature, that difference is not that much, but of course it is visible. It is visible as the temperature increases, that initial SOC that plays some role. Okay. Now comes the rate of charge discharge 0.5, 0.2, 0.1, 0.05. So which is basically from C/2 to C/20. Hardly there is any changes. All these are overlapping with each other because we are not considering C, 2C, 3C. If you consider that, we might have that impact more clearer. But we are on the safe side. We are on the safe side of discharging. So because of that reason, we didn't get much impact of this on the severity factor, which decides ultimately the end of life of the battery. So severity factor mean is calculated by averaging the severity factor values obtained under realistic conditions. Impact of temperature, SOC and C rate on the BS degradation is studied. So you see that severity factors having different values with respect to this temperature from January to the December. Again, if the state of charge is varying, how the severity factor is, mean of the severity factor is changing, and if the C rate is changing from C/2 to maybe that 0.95 of C, how it is the severity factor mean is changing. So that change is quite nominal, but I believe that beyond that it would be much more visible. It would be much more visible. So now my target is to find out the optimum operation of this battery for the for maximizing the battery life. Okay, so or at the same time minimizing the cost involved. So we are taking care battery life as one of the constraints. So my objective function is the cost involved of that, and there are several constraints related to that. So degradation cost is my objective function. Degradation cost is my objective function with some constants. So what are the constants? There is a power flow constant. So obviously, if you consider there is a PV power, there is grid and there is battery and there is load. So battery can be either act as a source or act as a load, depending on whether it is discharging or charging respectively, right? So you need to balance that power flow equation. You need to have that limit of that battery power. It should not be beyond this minimum and the maximum limit. You should have that SOC range. So it should be within that range of that SOC. You should have that capacity constraint. It should be maintained within this minimum of this remaining and the surplus during charging and during discharging, which is available and the deficit. The minimum of between these need to be taken, right? Is this clear? Minimum of what is remaining and what is surplus. So there could be a surplus energy which is the need of that system. But what is the minimum charge or the remaining charge in the battery? That maximum I can give. So the minimum of these two will determine the Q, that capacity of during charging module, and during discharging module, what is the available and the deficit. Minimum of that could be the deciding factor. And then there is some penalty factor violating of that constraints. So some penalty factor is being imposed. So these are the constraints, and with that constraints there are several optimization techniques, as Dr. Das was talking about. So we can use several optimization techniques for the purpose of optimizing any objective function. So here the objective function is that the degradation cost of the battery. So cost of battery is optimized using several heuristics of optimizing techniques, and the result which is best suited for the system consideration is found out to be this G-based and that ABC, G-based ABC, okay, artificial B colony, artificial B colony. But we have used that other also, that TLBO, teaching learning, and then IGWO, PSO with some modifications. And for different initial SOC, whether it is 0.2 or 0.55 or 0.95, we are having the best results every time we are getting with these GABC. Okay. So we considered that GABC as my choice of that optimal technique, and then we find out that with some fixed parameters, which is again tuned, and find out that what is the optimum parameters. Okay, the parameters are also tuned, and this found out to be the optimum parameter for that GABC. And with this tuned parameter, optimum parameter, the degradation costs are find out for different SOC level and different weather conditions. And thereby, if this that EDRP, that demand response policy, that incentive based demand response policy is adopted, then how much is the saving that we are basically showing through this table. And you can see that this is the degradation cost without outlier filter and without EDRP, means that what is the impact of the outlier filter. So earlier we have some kind of a study that without outlier filter we are using that LSTM, and then it is giving some forecasting results, and thereby we are getting that battery degradation cost. And then if that outlier filter is there, so the noises are eliminated through that filter, so obviously we will get some better result. Degradation cost with outlier filter but without EDRP, and then it is this the proposed one, the degradation cost with outlier filter and with EDRP, and every time we are seeing that this yellow bar is lowest, whether it is summer, mild or winter. Okay, so the degradation cost minimization is our objective, so we are achieving it quite satisfactorily if the demand response policy is being implemented in that particular system. Yeah. Now, if the forecasting tools are there, the battery degradation that minimization optimization policy is being implemented in presence of demand response, how this energy management tool will work? My God, this is not at all visible. But anyway, so we have that controlling code. So this is the grid operator or the utility algorithm. So how the grid operator will look into the system. So we have that login page. So it will ask first that are you user or grid operator? So this is the interfacing I am talking about, the front end, right? Are you user or grid operator? If say that okay, I am grid operator, and if say that I am user. So if it is grid operator, then it will ask that you select your location. So as I said that this particular project involves these 4 sites. So we'll select that Ghoramara or Keonjhar or Kitnos or Bonam. So I will select it. And then if I'm user, then I can use that, what is that user dashboard. So I can able to see that previous day or maybe in the previous month, how the things were, what the maximum incentives the people are getting if they are involving in the demand response or not. So I can have that intuition of taking part in the demand response. That's why this dashboard was created. So you have that ability to gain through some incentives, right? So you can go through that dashboard, and there is a master dashboard which is connected with this grid operator. So forecast matching with this that battery management system and the demand response, and then this user response for pricing and incentives, which involves this price, the incentive and the participations. So participation, there may be a few, it's basically optional that whether I'm taking part in it or not. Okay, so how many participations are there, then the incentive and the price can be decided, which is the discretion of this that grid operator or the utility end. But as far as that consumer end is considered, again that login page, and you were asked that whether you are user or the grid operator. If it is grid operator, it can able to match this master database and through this, but if it is user, then again from which location, and then you can have that through the master dashboard, you can have that user dashboard, which can be shown that what is my present load, what is the price for that particular load, whether I am taking part. I can able to see that what is the critical window for the demand response in day ahead basis, right? So during what period of time that demand response I can take part or not, and then the incentives, okay, and how much could be the monthly savings. I can able to see through this dashboard, or I can have that calculation in that interfacing itself, that by seeing my electricity bill and the previous year records, I can note down what was my monthly saving. So this is how the front end will work. So pricing, how it is decided? So there are 4 sites. So as I said that this Ghoramara and Keonjhar, they are having a fixed tariff independent of the units consumed, because we are providing the load, right? And we know that how much energy we are going to generate. So this is not a dynamic pricing. It's a fixed tariff. But this bonum and the Kithnos, depending on that historical values, generation and the operational maintenance cost and the other factors will decide that what will be the value of the price for this. And depending on that individual metering and that household and the critical loads and the commercial loads will have the pricing determination under this category. So category is also there for these 2 sites. There are categories that as it is said that what should be the tariff for this particular case, if it is household or if it is commercial. Okay. So it is considered that maybe that C1, C2 or C3 are considered for the demo purposes. It is considered that C1, C2 and C3, these are the 3 customers which belongs to this household, C4 which belongs to this commercial, and C5 which is basically charging. So this is he is owning the electric vehicle, so he is charging. Similarly for the Keonjhar also. So how it is decided? Again, that incentive mechanism, it's on the day ahead pricing. So whether there is a participation of that demand response or not, if it is not, fine, there is no calculation. So it's a fixed price. But if it is yes, then you can choose LR or LS, load reduction or load shifting. Okay, so 1 is referred to that load reduction, 2 is referred to that load shifting. So you can have that option of choosing that 1 or 2. जैसे मोबाइल में बात करने के टाइम पे we are having that option. So talk to the customer care, press 9. So it is something like that. Then if somebody is choosing that load reduction, right? So there is an option of reduction in the value in kilowatt hour and what time slot. So we are dividing the total time slot, whatever is in the day ahead basis. There is a critical DR and the non-critical DR. So you always can take part in that demand response, even if it is not critical, right? But your incentive will be less. Okay, it is B times of that price. Okay, so your electricity price is fixed. So whether it is A times or B times, critical, your A is greater than B. Of course, your A is greater than B. So final incentives with some different time steps, we can get that the incentives may be I or 0.8 I or 0.6 I and 0.4 I. What is that? It's basically, I am opening the slots for choosing your demand response participation maybe at 12 in the midnight. Okay, 12 in the midnight for the next day. So if someone is readily take part in that, then he will get more incentive. Okay, so total 24 hours is divided in 4 slots. 6 hours, 6 hours, 6 hours, 6 hours. Within the first 6 hours, if somebody is participating, he will get the full benefit of the incentive. But if you are in a dilemma that whether I will take part or not, so your action is delayed. So with that, you are getting some kind of a less incentive, 0.8 times the actual incentive, which is allotted. Okay, or maybe 0.6 times or the 0.4 times. So then, as soon as this demand response participation is decided as early as possible, it is easy for the operator to take action against anything. Okay, whether it is a normal or some disturbed condition. So that is why we are asking that you participate as early as possible. So it would be helpful for me and you will get more incentive. Okay, so that is the purpose of giving a different incentive, even if taking part for the same time window, even if it is a critical. And if it is load shifting, so this is for load reduction. If it is load shifting, that how much is the reduction value, the time slot, which is again depending on this electricity price. So C times, D times, E times or F times. So critical DR, non-critical DR for time slot this and for time slot this. Okay. So that is how that load reduction, the load shifting are considered. But of course, you will not get any incentive if you are not participating in the demand response. This is an example of these 5 different customers. The first customer is very rigid. He is not taking part in the demand response, right? Second customer have chosen 2 means is load shifting, not load reduction. So he wished to shift his load. And third customer, all the time he is willing to curtail the load. And the fourth customer, he is basically very fickle minded. Sometimes he is not ready to take part, sometimes he is ready to shift the load, sometimes he is ready to curtail the load and then change the mind. Okay. So all these kinds of scenarios have been considered. Again, similar scenario is for the 5th one. So all these different scenarios have considered, and then what is the participation in that demand with respect to the all timestamps, it is shown here for these different types of customers. So this will ultimately lead you to understand that how the energy can be managed, okay, in a day-ahead basis. So you have the forecasted load, you have that forecasted energy sources. You know the way that battery is traced because it is optimized now again, and how much is the participation of the customers with respect to the demand response. So the battery degradation cost will optimize, and at the same time the customers will get benefited because of that involvement in that policy of that demand response. So it's always a win-win situation from the operating point of view. It's win-win situation from the customer point of view. The both sides it's a win-win situation. So this is the policy which is now implemented in these 4 sites. Okay, what was being developed by our team. So what are the takeaways is that that energy management tool backend has developed. Front end still some work actually is going on. Inclusion of efficient consumer response, removing pricing and incentive techniques, one-stop platform for all 4 locations. Wherever we are using one single platform, and different consideration made for adaptability. You can adapt to any situation. Again, my special thanks, because not alone it's not possible. So these are the 2 ladies which were my BTech students. So through these UG projects, they have developed this EMT, right? So they worked like anything. So I was quite impressed the way they have handled this situation. So Vaishnavi was the leading one. Shreya was the supporting role. She played that supporting role. So she is the leading one, and she actually made all these changes related to this energy management tool. Initially, there was attachment as that JRF Kamini. But in between, she had some other work, so she left that. But the forecasting part and all, which was initially started with Kamini, and whatever the slides related to the battery degradation is entirely the credit goes to Dipanshu. So I give my sincere thanks to all these fellows. Because of them, this particular work related to this project is basically coming out to be fruitful in nature, and people are working this. So that's the great part. Thank you. Any question?
The ideal sample time for forecasting data.
1 hour.
What is the ideal sample time?
The available data is in 1 hour basis. So it's 1 hour. 1 hour.
Exercise has been done before the sample.
Yeah, the thing is that it depends on that how much is the cloud size, the recording and that storing that data. So and it is also considered that the climate has not changed so frequently, maybe within 15 minutes or 30 minutes. 1 hour is sufficiently enough for getting those data, as far as that renewable sources are considered, not for the load.
Because it will affect the efficiency of pricing.
Yeah, definitely.
Depends on forecasting of idealistically outside what we are forecasting flat
15 minutes.
15 minutes.
Because you are controlling, na?
My system accuracy will improve.
Yeah. You are controlling your plants.
Flat.
Here the sources are not controlled. It is controlled by God. You have no access to them. Nature.
Rate of degradation of capacity fades with respect to time. There is a characteristic.
Yeah.
That is regular in case of 10C, 6C, and 2C. But in case of C by 2, it is having some exceptional case. Is there any
Maybe 10C, 2C, 6C, this is all above your nominal rate of charge or discharge, but it is below that. So those two different windows are there because of that. I don't know, I may be wrong. Very fast, of course. So it is above that rated charging, and it is below the rated charging. So below the rated charging must have some safe kind of an that variation, and above rated charging, obviously the battery life will be much more affected because of that. Even if it is 2C and 10C, of course it should have, but they are pretty close. 10C, you can see it is far away from that.
In
Yeah.
case of 10C, the rate of decay is faster.
Yeah.
Then 6C, it is getting slower.
Yeah.
Then 2C.
Yes.
But in case of C by 2, it is exceptional. It is in between 10C and 6 in the character.
Let me check that.
So in the slide number 18,
Okay, so this one. Maybe I believe this should be C by 2 or what? Is the leveling anything is there? Yeah. But I don't know that this C by 2, 2C and 6C doesn't have much impact on it, but it is clear from that if you have that 10C, which is far more than that nominal charging rate, it has a different impact. So that is what maybe through this plot can be verified. So instead of C by 2, if you go for a C by 4 or maybe C by 10, maybe these are all clustered here, but 10C will have some kind of an more impact. But I believe that you change the battery, again the characteristics will be different, right? You take a different type of battery, the characteristics will be different. Temperature is, yeah. Yes. Anything else?
unavailability of the load forecasting data
Yeah.
is the only reason of using the two different tariff systems in that case.
Unavailability of the load data doesn't have any impact of this two tariff system, no. No. Keonjhar and Ghoramara are having two tariff system. That depends on that the societal the situation of that particular location. It's with the customers and the panchayat. They are mutually agreed upon of paying that much amount for these household purposes, for the commercial purposes, or maybe for the TV charging. So these were mutually decided. It was not that it was not available. There was no load. There was no load at all. So tariff is being mutually decided, and it was coming with that. So they are having two different states, two different locations, two different scenarios. The economic condition of these two different areas are different. So depending on that, it is decided. Okay, so I feel I'm on time.
Thank you, sir, for this
Yeah.
informative
Thank you.
information.
Thank you very much.
Now, let's join us